How to solve overfitting issue. So what is overfitting? Overfitting is when you train your neural network, the training error is okay, but the validation error have some huge gap to the training error. So although your neural network trained very well under your data set, but in reality, it performs very badly because the neural network just memorized the training data point and cannot generalize the prediction to other data point. Okay, so to solve the overfitting issue, to decrease this gap, there are many possible tricks. The first one, the most powerful approach to decrease the gap between training error and validation error is collect more data. The overfitting is also called variance error, which means our training vary a lot due to the training data point. So when you change some data point, some part of your training data point, your result, your obtained algorithm function, your obtained function will be much different compared to the previous case. So it is very sensitive to your training data point. Then you usually have high overfitting gap. Okay, so in that case, when you collect more data, so when you provide much more example to train your neural network, then even if the network just memorize the training data point, since there are huge reference, you can well generalize the output for any new input data. So collect more data. This is the most powerful approach to solve the overfitting issue. But the problem is collect more data means you need to pay something. So in some cases, this is physically impossible or costly impossible. But in that line, from the because of the physical difficulty or cost difficulty, many people invent some trick that looks like some data produce process, so which is called data augmentation. Classical data augmentation technique is just rotating your pictures or just change some colors or stretching or some shrinking your original image, cropping your original image, resizing your image, and so on. That is very classical data augmentation technique, because when you rotating or cropping a little bit, your main object never change. And there are modern data augmentation technique called mix-up or cut mix, cutout. This technique is very funny. Just add two different pictures and assign some mixed output label and so on. Then the input picture does not exist in real life, but this can provide very nice reference to train your neural network, and which can improve your generalization property, so we can expect very small overfitting gap. So that is the first approach to solve the overfitting issue. Either collect more data or introduce some data augmentation techniques so that it looks like there are much more data points. Okay, the second approach is use simpler neural network, decrease the width or decrease the depth. Then we have less parameter, So we can expect better generalization property. Okay, but personally, I don't recommend this approach because this approach can reduce the performance very easily. Okay, so instead of just decreasing width or depth, we can implement some other trick such that just keeping the width and depth and just decreasing the number of parameters. One possible approach is factorize the Wayne matrix. The factorization can keep the structure but can decrease the number of parameters, and from this technique we can expect some better generalization gap. The third one is some regularization cost or regularization trick for the optimization process. So usually we train our machine learning algorithm using this objective function, and objective function is function of your parameter vector or parameter matrix beta, right? The ideal machine learning framework will find out the optimal beta that minimize the objective function L or loss function L. Okay, but this optimal point can have high generalization gap. So to resolve this issue, we can think some suboptimal point beta hat such that L beta hat minus real optimal point minimum beta L beta is not equal to 0, but have some gap. And this optimization gap can decrease the generalization error. So to increase the optimization gap, we can introduce some early stopping rule so that before convert to the optimal point, we can stop, so we can have some high optimization gap, and from that we can expect some better generalization error. The SGD with large step size, which also cannot provide the optimal solution because the SGD has some noise at each epoch or at each iteration, and constant step size will move with noise direction with constant amount. So usually SGD with large step size cannot converge to the optimal solution, and which always have some gap, optimization gap. And the optimization gap can solve the overfitting issue a little bit more. So SGD with large step size itself also very nice generalization technique. We can introduce some cost function, some additional function C, and solve this new optimization problem. Because of this additional cost function term, when you solve this, your solution beta star will have some optimization gap. Why? Because we are solving some different optimization problem compared to the original one. Actually, the weight decay method comes from this, comes from the cost function summation over the square of each parameter. Okay. The last one is some noise addition. The most representative example is dropout. So when you train your neural network, instead of using the original neural network structure, at each iteration, we randomly remove some edge or randomly remove some neurons so that the neural network contains some artificial noise, and the artificial noise can prevent the convergence to the optimal solution of your objective function. This obstacle for your optimization process, this is not good for your optimization, but this is good for your regularization and the generalization gap, right? And very recent technique, Bettinum, which also introduced some artificial noise, because the Bettinum, I will explain the details of Bettinum in the later week, but briefly, the Bettinum also introduced some additional artificial noise to each layer so that the optimization process cannot converge to the real optimal point, and which basically can improve the generalization gap.